Hello, Vanakkam. Welcome to the Electrical Engineering Examples channel. I have created this channel in order to solve numerical problems that you commonly encounter in electrical engineering. The main objective of this channel is to provide you an elaborate solution that I expect you to follow during exams in order to maximize your performance. I hope you will learn from this and you will use this during exams. In this video, we will look at a question that is related to a synchronous machine connected to an infinite bus. The synchronous machine that we will be looking at in this video is a cylindrical rotor synchronous machine, which is widely used in thermal power stations, in nuclear power stations, as well as in gas power stations. So here is the question. A three-phase 18 kVA, 220 volt, 4-pole, star-connected cylindrical rotor synchronous machine has a synchronous reactance value of 1.75 ohms per phase. The resistance of the stator winding is negligible. The machine is connected to a three-phase 220 volt infinite bus. Neglect rotational losses. The field current and the mechanical input power are adjusted so that the synchronous machine delivers 10 kilowatt at 0.83 lagging power factor to the infinite bus. Under this operating condition, determine the excitation EMF and the power angle. There is another part to this question, part B. And in part B, with the excitation current held constant at the value found in option A or part A, the driving torque, which is the input to the synchronous machine, is reduced until the generator is delivering 8 kilowatts. Determine the armature current and the power factor. So this question has two parts to it. Part A is one needs to determine the excitation EMF, which is symbolized using block letter E, and the power angle, which is usually represented using the symbol delta. And in the second part, one needs to find armature current and the power factor for a different operating condition. So in this video, I will try to solve this example problem in a step-by-step manner so that you can easily follow it, and hopefully you can solve similar problems without much difficulty. The first step in solving such problems is to represent the given system in a pictorial form, especially using per phase equivalent circuit or using a single line diagram, whichever is more convenient, whichever is more appropriate. In this problem, I am going to represent the given system using a per phase equivalent circuit. So here, representing the given system using a per phase equivalent circuit, I will have the following diagram. So the synchronous machine is usually modeled using an voltage source, which is the internally generated EMF, with an impedance in series, Now, since in the problem statement, the stator winding resistance is indicated as negligible, I have excluded it completely, and I have just drawn the synchronous reactance JXS. And here I have my excitation EMF, which is nothing but the internally generated EMF, is usually a vector. This is the synchronous machine. Okay. And this synchronous machine is connected to an infinite bus. And since the infinite bus is consuming power from the machine, I'm going to represent a load or an infinite bus using a load. So the load at the infinite bus. Please note, across the terminals A and B, there is an infinite bus, which means the voltage across the terminals is fixed at whatever value is specified in the problem, and the frequency of this voltage will also remain constant. Now, if a synchronous machine has to supply a particular voltage at constant frequency, the only way that can happen is if the speed of rotation of the synchronous machine does not change with time. Therefore, the moment we have a single machine connected to an infinite bus, we know for sure that the speed of rotation of the rotor of the synchronous machine cannot change with respect to time. So the speed is fixed, that is determined by the frequency at which the voltage is generated, as well as the number of poles the machine is built with. This is a 4-pole machine, and since we do not have the frequency information in this problem, we cannot determine the exact synchronous speed. Nevertheless, we can be certain that the speed at which the machine rotates will always remain constant. Okay? Now, coming back to the pictorial representation, here I have the internal generated EMF. Let me draw this symbol a little bit closer. This is a vector, which means there is a magnitude and an angle, and the angle is nothing but the power angle delta. And then, because the stator winding resistance is neglected, the series impedance gets modified into a synchronous reactance. So I'm just going to mention that stator winding resistance is neglected. So this is note number 1. Note number 2, since the frequency and voltage, since the voltage magnitude and frequency of the voltage are fixed at an infinite bus, the speed of rotation of the synchronous machine is also fixed. Okay, so this is something I would like you to keep in mind. In fact, I don't have to write this voltage magnitude. I'm just going to focus on the frequency. That way it is clearer. Since the frequency is fixed at an infinite bus, the frequency of the voltage is fixed at an infinite bus, the speed of rotation of the synchronous machine is also fixed. It's also constant. It will never change with time. So this is an important point we need to keep in mind. Now, in the problem statement, there are two sets of information that are specified. The first line on top, this information corresponds to the rating of the machine. Okay? Whereas the line here specifies the operating condition of the system. Okay? Now, what we are interested in is the operating condition of the system more than the rating of the machine. Okay? So that is something you need to keep in mind. So based on the operating condition specified in the problem, we can say that armature current will be flowing in this direction from the synchronous machine into the infinite bus, and the power consumed by the load, the real power indicated by the symbol P with the subscript load, which is infinite bus, is 10 kilowatts. And it is also mentioned that the power factor, which is nothing but the cosine of the angle between the load voltage and the load current in per phase, is given as 0.83 lagging. Now, since this is a series circuit, the load current is same as the armature current. Now, assuming the load voltage, which is nothing but the terminal voltage of the synchronous machine, as the reference phasor, as the reference quantity. What do I mean by that? I mean V vector is going to be equal to V magnitude at an angle 0 degree. Now the 0 degree comes because I have assumed this load voltage quantity as the reference quantity for the whole system. And the load voltage magnitude is specified in the problem as 220 volts. And therefore, this is going to be my voltage across the load. Now, in the problem statement, it has been mentioned that the power factor, which is nothing but the cosine of the angle between the load voltage vector, load voltage phasor, and the armature current phasor, is 0.83. And it is said to be lagging, which means if I drawing the phasor diagram at the load, my load voltage will be my reference, which is 220 at an angle 0 degree in volts, and the current IA, which is also the load current, is a vector, and it will be lagging the load voltage by an angle, let us say theta. This theta is nothing but cos inverse of 0.83. Please note, because the power factor is lagging, my current is drawn like this. If the power factor were leading, the current will be leading the voltage. Always the current will be lagging when the power factor is lagging, and the current will be leading when the power factor is leading, based on the assumption that we have made that the voltage is going to act as the reference. That is something we need to keep in mind. Now, what is cos inverse of 0.83? So I am going to determine the angle theta. Theta is cos inverse of 0.83, which is 33.90 degrees. Now, when I represent the load current, which is also the armature current, because it's a series circuit, in complex form or in vector form, my IA vector will have a magnitude of current, and there will be an angle theta. Now, because this angle is corresponding to the lagging angle, we are going to indicate that using a negative sign. If the current was leading the voltage, then we would have had a positive angle. Now, why is this correct? In electrical engineering, we always take counterclockwise direction as the positive and clockwise direction as negative angle. Okay. Therefore, this is the magnitude of the angle theta, and it is given in clockwise direction, which implies when I write the armature current phasor, I will have a magnitude for armature current with an angle theta with a negative sign. So I'm going to write the negative sign indicates that the current is lagging the voltage. Okay. Okay. I think I made one small mistake in the voltage magnitude. Let me just go back to this slide. So here we have drawn the per phase equivalent circuit. Therefore, this voltage will not be 220 volts. It will be instead 220 divided by root 3 volts, because 220 is the line to line voltage in any problem that is given. So we are going to divide it by root 3 because the system is a star connected system. If the system were delta connected, we would have retained the value as it is. So that is a small correction I need to make. So I will just rewrite that here or include it here. Okay. Now, with this value known, let us now calculate the magnitude of armature current. Now, when we connect a single machine to an infinite bus, the power consumed, the real power P, 3 phase, is given by this expression 3 times V phase I phase cos theta. Okay. Now, for the given system, the given 3 phase power is 10 kilowatts. That is equal to 3 times the phase voltage is 220 divided by root 3. Current magnitude is something that we do not know, and cosine of theta is nothing but the power factor itself, which is 0.83. And please note, power factor is just a magnitude. So here we are not bothered about whether it is lagging or leading. It is just the magnitude that we are interested in. So solving this, I can get the value of IA. So IA is going to be 10 kilowatt divided by root 3 into 220 into 0.83. So this is nothing but 31.62 ampere. This is the magnitude of current flowing into the infinite bus when the machine is supplying 220 volts or maintaining 220 volts across the infinite bus, and the power factor is 0.83 lagging. So the current phasor is 31.62 ampere at an angle of negative 33.90 degrees. It's very important that you do this analysis this way. So let's go back a couple of steps. So once we know the question, we are making sure that we represent the system using a per phase equivalent circuit diagram. And we have across the terminals A and B is the infinite bus. And because it's an infinite bus, the load voltage cannot change. It is fixed at a value. Now the value of the infinite bus load voltage is 220 divided by root 3, because this is a 3-phase system as indicated here, the 3-phase star connected system. Okay. And therefore, we will have to maintain 220 divided by root 3 as the phase voltage. That is why it's 220 divided by root 3. And I'm assuming the voltage at the load, across the load, as the reference quantity. And that is why I have the 0-degree angle here. Once I assume voltage as the reference, based on the problem statement, I get the phasor relationship between the voltage and the load current, which in the circuit also happens to be the armature current. And the armature current is nothing but something that we can obtain using the power equation. So the total power consumed by the infinite bus divided by 3 times the phase voltage, which is 220 divided by root 3. I cancelled out the root 3 and 3, and I got it as root 3 times 220 times the power factor value, which is 0.83. And when I solve it, I have 31.62 ampere. So the armature current that is flowing out of the machine into the infinite bus under the specified operating condition is found to be 31.62 ampere at a negative 33.90 degree angle with respect to the reference phasor, which is the load voltage phasor. I hope it is clear until now. Now, our objective is to determine the excitation EMF E and the power angle delta. Now, if we go back to the equivalent circuit, redrawing the equivalent circuit, I have my internally generated EMF, E vector. I have my JXS. I have my two terminals A and B, across which is the load. V load as a vector is known, and the current that is going into the load is nothing but the armature current as a vector is known. Now I can apply KVL in this loop. So in this loop, I can apply KVL. So this is, let's say, loop 1. So applying Kirchhoff's voltage law, I have my E vector equal to IA vector times J times XS plus V load vector. Now E vector by definition is nothing but a magnitude E at an angle delta, and this is what we want to solve. IA vector, we found it to be 31.62 at an angle of negative 33.9 degrees. J times XS is specified in the problem as 1.75 plus V load is found to be 220 divided by root 3 at an angle of 0 degrees. I merely have to solve for this complex quantity E to get the excitation EMF and the power angle delta. So solving the above equation, I have my magnitude E and delta in degrees is equal to, let me quickly use my calculator. I'm using a calculator which can solve complex numbers. So you are free to use such a calculator in exams. So I'm getting a per phase excitation EMF as 164.425 at an angle of 16.22 degrees. This is the excitation EMF, the unit of which is volts, and this will be per phase. So if you want the three-phase excitation EMF, you need to multiply this with a factor of √3 because that will be the line-to-line voltage. But we will usually work with per phase quantities. Okay. So this completes part A of the question. So part A asked us to determine the excitation EMF E and the power angle. We have solved for both of that. So the procedure we followed is we solved for the load current, which is nothing but the armature current phasor by two things. One is using the power that is specified in the problem, as well as using the power factor value that is specified in the problem. Now we have to move on to the next part of the problem. In this part, it states with the excitation current held constant at the value used in A, the driving torque is reduced until the generator is delivering 8 kilowatts. Determine the armature current and the power factor. Okay. Now it's important that we understand the first part of the first sentence of this question very clearly. So let me just focus on it a little bit. Say it states clearly with the excitation current held constant at the value used in part A. What does this imply? Now please note, since the synchronous machine itself is rotating at a fixed speed, the magnitude of excitation EMF E will be determined only based on the excitation current. If you recollect the open circuit characteristic curve of any synchronous machine, so if I draw the open circuit characteristic curve or the magnetization curve of a synchronous machine, it is nothing but it is the plot of the magnitude of excitation EMF E, which is also known as the internally generated EMF, versus the field current IF for a particular value of speed or for different values of speed. And usually it is like this, right? And this is for a particular value of speed. Okay. Now, because the synchronous machine is connected to an infinite bus, we know that the speed at which this machine is operating cannot change. And therefore, if in the problem statement it says the field current value has not changed from the value that is used in part A, we can very well state the excitation EMF magnitude also does not change. Therefore, for part B, one can very clearly understand that the magnitude of excitation EMF E does not change from the previous value, from what was estimated in part A. Please note, it is only the magnitude that does not change. The angle, which is the power angle delta, can definitely change depending upon the operating condition. So that is something very important you need to keep in mind. So the speed does not change because the machine is connected to an infinite bus, and at an infinite bus, the frequency cannot change. And since the speed and frequency are directly dependent, the speed cannot change. Now, if the field current value also does not change, IF also does not change, then it is evident that the magnitude of excitation EMF from part A cannot change. The power angle delta, it can take any value. Now, what does the problem statement say? The problem statement says for part B, for the same value of excitation EMF, the driving torque to the input of the synchronous machine is changed such that the power output at the generator terminals is now only 8 kilowatts. So power input is changed, basically reduced. The rotational losses are already neglected, so we don't have to worry about that. If the rotational losses were not neglected, then as the input power changes, probably the rotational loss might change, might not change, depends on the system. Okay. Rotational losses are neglected. The power output at the synchronous generator or power output at the infinite bus is now only 8 kilowatts. Okay. Now we know for a synchronous machine connected with an infinite bus, three-phase power, real power P, it can also be expressed using this expression 3 times V phase magnitude, excitation EMF magnitude divided by excess sine of the load angle delta. This equation is valid for a synchronous machine that is connected to infinite bus, and if the stator resistance is neglected, which is the case in our problem. So for a synchronous machine connected to infinite bus, and if the stator resistance is negligible, we know we have derived in lecture an expression for three-phase power, which is P three phase is equal to 3 times V phase E excess sine delta. Now substituting the values of V phase, which is nothing but the load voltage. So for our problem statement, it is 8 kilowatts, which is equal to 3 times 220 divided by root 3 into the magnitude of excitation EMF from part A. It has not changed. Okay. So we have to recollect that is 164.464 or 465, and this whole thing is divided by excess, so that is 1 over 1.75. Please note it is just the magnitude that we are considering, times sine of the load angle or the power angle delta. So in this expression, I know everything except for the value of delta. I can solve for delta. Solving for the power angle delta from the above equation, from the previous expression, I have delta is equal to 8 kilowatts divided by root 3 into 220 into 164.465 divided by 1.75. So I have to sine delta is equal to this. I have to do sine inverse of that to get delta. So let me do that in my calculator. So 8 kilowatt divided by root 3 into 220 into 164.465 divided by 1.75. If I do a sine inverse of this, I get 12.91 degrees approximately. So this is the new power angle. So what has happened is, by maintaining the same field current and by reducing the mechanical input to the synchronous machine and by reducing the power delivered to the infinite bus, the magnitude of excitation EMF has not changed, whereas the power angle delta has gone down from 16.4 degrees to 12.91 degrees. This makes sense because as the output power is reduced, the delta value goes down. If the output power had increased, then the delta value should have gone up from the previous value. Okay? So this is the value of delta. Now the objective of this question is to solve for armature current and the power factor. Now to do that, we have to go back to our equivalent circuit. So let me just quickly move this a little bit. Redrawing the equivalent circuit. I have my excitation EMF magnitude and the angle which is known to me at an angle of 12.91 degrees. This is the internal EMF. I have my JXS, which is J1.75, and I have my terminals connected to the infinite bus. So this is A and B. And now there is still a load type at the infinite bus. The power consumed here is P3 phase is equal to 8 kilowatts. Okay? And the voltage at the load, which is the infinite bus, is not going to change from its value, which is 220 divided by root 3 at an angle of 0 degrees. I know what is JXS, which is J1.75. So let me just replace that. So I have access to all the values. All I need to do is to solve for my armature current phasor, which is IA. So IA phasor can be obtained by applying KVL to this loop. So applying KVL to the circuit, my IA vector can be thought of as E phasor, which is magnitude E at an angle delta, minus V phasor, which is magnitude of load voltage at an angle 0, divided by J times XS. So that is 164.465 at an angle of 12.91 degree, minus 220 divided by root 3 at an angle of 0 degrees, divided by J times 1.75. So solving the above expression using my calculator, let me quickly do that. I have my current value as the current phasor is 28.333 with an angle of negative 42.18 degrees in amperes. Okay, so this is something very important, very interesting. Okay. So just let us take a moment to redraw the phasor diagram of both the conditions. So this is the final, this is the magnitude of current. Okay. So this is the current value that we have got, 42.18 is the angle. Now the power factor. Power factor is obtained by taking the cosine of this angle of current, because the voltage of the load is taken as the reference and power factor at the load. So power factor is equal to cos of 42.18. So let me quickly do that. Which is 0.7417 and this will be lagging the voltage. So it's very important that when you solve for power factor, you indicate whether it's lagging type or leading type, without which you will lose a few points. Okay. This completes the requirements of the problem. Now, what I would like you to take a moment to observe is, let us quickly sketch the phasor diagram for operating condition part A and operating condition part B. In both cases, the load voltage, which is the reference phasor, is here. Okay. In case A, my current IA is lagging the load voltage by an angle of negative 33.91 degrees. Okay. And the magnitude of this current, I want you to look at the magnitude of the current. It will be 31. So let's quickly go back. It's a few slides behind. 31.62 is the magnitude. 31.62 ampere. Okay. And the excitation EMF E was found to be 164 at an angle of 16.465 or something degrees. Okay, 16.4, let's say. I'm not being precise, but that's okay. Now, when the output power decreased for the same field current, the magnitude, which represents the length of this vector, has not changed, but the angle has changed to 12.91 degrees. So the length of the vector has not changed. The length of the vector has not changed. E magnitude has remained the same, but it has gone closer towards V load. And consequently, you will see that the current value has gone wider. It has now become minus 42 degrees. So it's minus 42 degrees. And the current magnitude is 28.333 amperes. Okay. The magnitude of current has gone down, but it has gone wider than what it was previously. So 28.333 amperes. So this is something I want you to keep in mind. So what happens is, as we fix E and change the input power, okay, current changes, the magnitude and the angle has changed. In the next lecture, I will be introducing a new topic where we will try to fix the input power, but we will try to change the excitation EMF of the synchronous generator. And we will see what happens under such circumstances. Okay, so this problem has helped us utilize the concept of a single machine connected to an infinite bus successfully to solve for the excitation EMF and power angle under a particular operating condition, as well as an armature current and power factor when a few operating conditions are changed. I hope this video has helped you learn how to solve such an example or such a problem, and I hope you will follow the detailed steps that I used while solving this in your exam as well. Please make sure you write your explanations before you solve any equation. Okay? Thank you so much. I will stop here.